today's lecture, we're going to see how to use Z transform connected with a linear time invariant system. Particularly, we're going to use the fractional format of a Z transform to explain a linear time invariant system. And then we go to some practical LTI systems expressed in Z transform. And then we will, during this class, to find a way to find the inverse Z transform. So convert it back from the Z domain back to the time domain. So last time, we look at a system. System block diagram is that I have an input xn, output yn. The system is identified by the impulse response hn. Therefore, in the time domain, we have a formula which is a convolution. Yn equals to hn convolved with xn. And the convolution is valid. The precondition is that I need to have a linear time invariant system. So this is important, LTI system. Once it's LTI system, we know we can define a convolution. LTI system is easy to analysis, and most practical systems can be divided into piecewise linear system or piecewise LTI system. Therefore, we can use this technique. In the Z domain, when we translate into another transformation domain Z, the convolution becomes a product, So we have YZ equal to HZ times XZ. So it becomes a very nice format. The reason we like that is because it's easy to manipulate YHZ according to a product. So the system H can be easily calculated as Y over X, YZ over XZ in the Z domain. Here, HZ, we know that's the Z transform from the impulse response, and we call that the system response. So HZ is a system response. System response, HZ, equal to that. And then the rest of the work to do is to find the inverse Z transform HZ. So from HZ, we need to find HN. So once we got that, we can identify the system or find the system. And this is given by any arbitrary input and output. We don't need to excite the system with an impulse. Specifically, if you can do an impulse and then the output, if I have an impulse excite the system, and then the output is simply the system response or the impulse response, HN here. However, if I don't have that, I don't have an impulse. I have something that naturally with an input signal xn, and I observe yn. So these are all arbitrary signals, hn, yn. But with these arbitrary observations of just one shot, I will be able to use that to calculate capital H and then find the impulse response. So this is how we deal with a system in the Z domain. Now we know for a linear time invariant system, it can be described by a constant coefficient difference equation. So the system can be expressed like that. We already know that. It's a difference equation. So we have the current output Y, that's what we have at the observation. We have the current output Y is equal to, these are the feedbacks. So I have all these Y's are put in memory. And my system is called order of capital N because I need to have N memory spots in the system to store all these N outputs, Y, N minus 1, N minus 2, all the way to N minus capital N. And these memory registers or memory spots, if you like, they will be weighted by a coefficient A. And we call this feedback. And then, of course, we have this input. The input are all these X, but we have the current input, Xn. We also have previous input, all the way to Xn minus capital M. And these m inputs are also affect my current output yn. So what we can do is we can calculate these in the z domain. So we have yz, and get everything here is in the z domain, z transform a linear transformation. So can work with that on each individual terms here. And then according to the shifting property, we know this delay can be expressed in the z domain, which is yz times a term z to the power negative k. That is my k time unit delay. All right, the reason we are trying to do this, because now we have extract an individual yz, an individual xz. We would just pull this out of my parenthesis, Then I can very easily to write out hz equals to yz over xz, and then bring this parenthesis to the right of my equation. We have this term. And this is only a format of coefficients b's and a's. There has no y or x, there's no h in it. All this hz, the system, is on the left of my equation. Okay, so we simply calculate that. Now, if you look at the last format, this is a z transform in a fractional format. The numerator is a polynomial, denominator is a polynomial. That's a polynomial b as a function of z to the power negative 1 over a polynomial in the denominator, polynomial a, as a function of z to the power negative 1. Or as a function of z, it doesn't matter. It's z to the power, it's just inverse. Fractional term that directly corresponds to our difference equation. Difference equation is what we have to describe an LTI system. So that connects very well. We know that we can use a constant coefficient difference equation to represent an LTI system. We can also use a rational system function hz to represent an LTI system. It is written in this box. Once I know those constant coefficients a's and b's, I can write out the system function. So for this system as a rational system function, we have the numerator, denominator. Now for the numerator polynomial, we can find all these zeros. Zeros meaning that I take the variable z equals to zeros, and then the numerator becomes 0. And what I have here is at that time, hz, this guy becomes 0. These are called the zeros. Zeros are the complex number that make hz equal to 0. And we examine the denominator, we find out some poles. Poles is defined as z is equal to p sub k. If I am taking the z at those numbers, which is the root of the denominator polynomial, and then we have this hz, we join into a pole, but this pole is kind of upward, so hz is infinitely large. Okay, so we have 0 in the poles of a rational system function in general. In some particular case, we can have, first we have called all zero system. All zero system meaning that I only have 0, but no poles. Therefore, my rational system function only has the numerators, does not have denominators. So we have here, we have hz only has this polynomial on the numerator. Denominator are coefficient of a's. But for the denominator, everything except the first one, except a0, by definition, we always try to normalize that. This is 1. But all the other coefficients, ak, when k is from 1 to n, those are all zeros. Therefore, the denominator is just 1. So we don't have that. We have a polynomial here. And we can write it, if you want to write as a polynomial of z, we pull this out. We write it like that. So this system has m non-trivial zeros and m trivial poles. So we need to emphasize, theoretically, we have the same numbers of zeros in the poles. But those poles are not shown, or actually those poles are at at z equal to 0, trivial zeros. If you really want to put into this format, now this is a polynomial, and these are the poles, right? These are the m zeros when z evaluate at 0. We got that. But if you just look at this equation as a function of z to the power -1, and we find that we have m non-trivial zeros, meaning that those are the zeros not at origin. This is an all-zero system. Well, all-zero system, what is that? Well, that's a finite impulse response system, right? All-zero system is finite impulse response system. Why is that? Well, for this guy, if I'm doing an inverse Z transform, it's very simple. I'm doing inverse. I'm trying to transfer this back to Hn. So on the right-hand side of my equation, this guy will become B. What is that? That's B0 times Z to the power -0. That's 1 plus B1 delta n minus 1 plus B2 delta n minus 2 all the way to Bm delta n minus m. So what we have here is we just have all these delays, Now, if I am putting that as yn, simply yn is just B0 xn plus B1 xn minus 1 plus B2 xn minus 2 and all the way to Bm xn minus m. Okay. And we have, this is a convolution. Convolution coefficients are exactly those b's. So we have this parameter vector b convolved with parameter vector of x, and then we got output. This is a finite impulse response system. And you can actually take all these, like we like to indicate these as h0. If I'm just putting parameters h1 like this one, h2, and then the last one here is hm, then it's just a convolution, and we have a finite impulse response system, right? All these, the response is finite with m, and then do the convolution. Okay, we also call that a moving average system. Why is that a moving average? Well, you basically average all these input signal x. You average all these input signal x, but within a window of capital N. And this window will move because when you take different time n, this window will move, but it's a window of m, and it just weighted by all these b's, all these h's, you weighted. So it's a moving average. It's called MA system, FI system or MA system. FI system has been used a lot in filter design. The good thing about it is because it's easy, it's just a one convolution, and because it is finite, so all the FIR system are stable system. All the FIR system are stable system because there is no feedback loops. So I don't have the danger that my system will bust. It just have finite input. The output will always be finite. Okay. The second special case is called a all-pole system. All-pole system, that's easy to understand. All-pole system is that I do not have numerator. I only have denominator. So the numerator is B0, take that as 1. I just leave it B0. I don't need to normalize that term, just as constant. All the other, this is not 0. All the other terms are zeros. Therefore, the numerator becomes just B0. The denominator is a polynomial of z to the power -1. So we have that with all these parameters a's. For this system, you can also write it as a function of z. If you write it in this format, you find out I have exactly the same numbers of zeros on the poles. But in this case, just I have n trivial zeros. meaning that all these zeros are at z equal to 0. We'll make this part equal to 0, right? And I have n non-trivial poles, which is showing in here. Right? This is a all pole system in a normal format. If we write into this format, and I'm only counting these non-trivial poles, and we find out I have only poles, there's no 0. It is all pole system. All pole system itself is an infinite impulse response system. So if I really want to write my output as a convolution of some input coefficients, let's say y0 or h0, h1, n, xn minus 1, plus all the way go hm xn minus, I'm using ms before, but I will not stop here. I need to write more things. Actually, it will be infinite many of those terms. I need to have infinite many of those terms if you want to write out just a first order, a convolution like that. And this is an infinite impulse response system. What is impulse response? Are those H's. So these H are, it's never ending. In time, I got 0. These are H0, H1, H2, but it never ends. It's infinite many of those impulses. So it's IR system. And we also call that autoregressive system, called AR system. Autoregressive, the name is coming from the fact that I have all these feedbacks. Now, what are those A's? Those A's. These are the A's that's we are working that on y, right? If you write this as yz over xz, so yz is multiplied by that, x is multiplied by this numerator. So we have a regression, we have a regressive, which are the feedbacks of all the output y's. So that is here. Now, what we have in the system is yz times sum of ak z to the power n. Let me using this one. So this multiplied by 1 plus sum k from 1 to n a k c to the power negative k equals to b0 times xz. It's very simple on the x part. So we take an inverse z transform. In this case, it's quite simple because everything is just, we don't have a denominator. It's just in this polynomial term. So we have yn plus a1 yn minus 1 plus a2 yn minus 2 to an yn minus n equals to b0 times xn. Okay, that's it. That's it. So if you move all these y's as a memory to the right-hand side of my equation, we just have yn equal to negative sign of all these a's weighted by a's of the y's plus b0xn, autoregressive, because I'm taking the feedback of y. It's a regression of the system. An all-pole system is very useful in practice, and people like to use that for a predictor. For example, if people have some voice signal, I know all these sample points. If suppose I sample dense enough, or any curve, people are trying to predict some curve, some linear curve of functionality, predict some curve of events happening, predict some financial curves, for instance. So you have all these points that previous. What I want to find is I want to find out the future point, this one point. Sometimes it's called one step further. You want to predict one in the future. Sometimes maybe you want to predict a few of those. This is prediction. So everything here is that belongs to the same function. So in our case is my y. So I want to find of yn in terms of that will be a sum of these previous y's, yn minus 1, suppose I have already observed all these points, yn minus 2, and then go all the way yn minus n, right? That's what I need. That's prediction. That's prediction. Now you'll say, well, what do you have for this term, x term? Well, usually that is a prediction error. So when you do a prediction, this is something that you have after your model, and you can have some actual numbers, but there is an error, so it's a prediction error. Now we can train this entire model. So let's say I have y negative 100 to y negative 2, I get y negative 1, and you observe that. So you plug into your equation and you train the model to find out what are those coefficients a's. And then you do it again, you move the window. Eventually, after you get more and more data, you have a much better sense of all these coefficient a's. During the time of training, whatever you observed and compare with the true value, there is an error, right? There's an error. That's your prediction error. Now, the goal, or how do you build a model, is to minimize your error. Usually, well, as I was saying, you take in, maybe you take in a lot of those numbers from 1, 2, 3, 4. You take many of those. What you want to do is trying to find all these coefficients a's. But during that time, you will generate a group of those errors, en, where n is also the 1, 2, 3, 4, and etc. What you do is I want to minimize the error, usually in a mean square error sense. So I want to minimize this, and you can do an expected value, or if you take a block of data, it just simply sampled. You sample 1 over n, where you sum over n, that's e of n, absolute square, so it's mean square error. To minimize that, in order to find all these coefficient a's, ak's, to find these, and then you have a very nice prediction model. Okay? And then you have a very nice prediction model. You got these a's, then you have a new set of y's. You can predict a future y. So it's a predictor. How do we implement that? We are using an AR model. So usually that's what we do for prediction. So this is just a big picture, basic idea. Predictor, if you dig into that, you'll find out, well, it's very nice because everything we can analyze that either using a difference equation or put into Z domain. Z domain is an output system. You find these coefficients. You can discuss about the system stability and many different properties. Okay. Another system is called a post-zero system. Post-zero system is the one that combined the previous two. So I have both poles and zeros. I have a complete rational format for this transfer function, for this system function. In general, the system function contains n poles and m zeros. The poles and the zeros at those trivial numbers, which are mathematically, I should have exactly the same numbers of poles and zeros. But I usually don't count the trivial poles, or I don't count the poles and the zeros at infinite. Infinity is also one point in a complex plane. Those are implied, but are not counted explicitly. Therefore, I have n poles, m zeros, and then m can be different. Due to the presence of poles, a zero pole system is an FIIR system. It's an infinite impulse response. Because I have poles, I have denominator. The pose is generated by a of z to the power. It's generated by this term. And that is the feedback, because yz over xz, this is my hz. Okay. You multiply around that, so it's yz times a z times this polynomial. And then we know this part is the feedback part. And I have xz times this part is the feed forward part. Because I have feedback part, the system is infinite impulse response system. And impulse response is you convolved with X. Now this is really somehow combined with output Y. If you want to calculate or find out what's the same effect of that something convolved with X, well, you have infinite many of those. So it's an IR system, right? Impulse response is basically something you convolve with X. Okay, so these are some special cases, all zero system, all pole system. And more in general, that's a zero pole system. That is how we deal with the linear time invariant system using a fractional rational format to represent that. The only problem left is we are trying to find the impulse response Hn. We're trying to find this. We already said if it's a fractional or rational format, y over x equal to yz, we should be able to calculate this very easily. In Z domain, that's a division. And yz is something that we observe at output. Xz is observation at the input. So I should be very quickly to get these values. And then you divide that, you find a Hz. Then we need to do an inverse Z transform to find the impulse response in time domain. We know that inverse Z transform is a counter integration, right? We wrote this before. Where the integral is in the complex domain, it's counter integration. And the counter integration is such that I take its integration over a closed path C that encloses the origin and lies within the region of convergence of Xz. So let me draw the picture here. Let's see what we meant by that. Usually, this is how a region of convergence look like. In general, it is larger than a radius. Its mole is larger than the radius R1, smaller than another radius R2. And you can argue there are some special case. If these are zeros and if this is 0 and you deform that into just one big circular area, if this deform into infinity, and then you have the exteriors of a circle. And if these two, they somehow, this point, the mole of this point or this radius is larger than the radius of this point, then this region of convergence deformed to an empty set. So there's basically that's the Z transform. I cannot do that. Right? But in general, it looks like that. And then when you do the counter integration, is that you have to move within the region of convergence, because out of that it's undefined, or it is EO defined. And within that, you need to do a counterclockwise path that encircles the origin, and end up with your starting point. You follow this, you take all these Z values on your path, do this integration, and you will find out the inverse Z transform. And that's a little involved to do because we really don't want to do an integration in the complex domain. So let's see what we can use some other method to do that. Common methods for inverse Z transform. We can do first is, of course, by brute force, doing the counter integration. The second method is to do a power series expansion, use long division. So because what you have is you usually Hz is in this rational format, Bz over Az. These are two polynomials. So what I can do is I can do a long division. But the only problem is that when you do a long division, there may always be some remainder. Okay. Now I want to make this equal to another polynomial, but somehow you will have a remainder if the order of B, the remaining part, let me call it prime. When the order of B prime is smaller than the order of A, you will still have this rational term. It's not going to write out into a very nice polynomial term, so, right? So the long division has some problems. And then we have our third method is doing a partial fraction expansion. Partial fraction expansion, and using that to find out the inverse Z transform. So the partial fraction expansion, you can think of it's coming after the long division, like doing this. We already move a very complicated rational format into these, into a polynomial and the second term here. The second term here is that I have the order of denominator a's are larger than the order of numerator. And then what I want to do is I want to either do a simple calculation, or if this denominator has order of just 1 and 2, I can look up the table. Do you remember the Z transform table? When we did before, right? We said that the Z transform table denominator of order 1 and 2. If we move beyond that of order 3, I can always break down into smaller orders. So we would kind of have some recall something like that, but we don't remember very clearly. Let's see what we can do with some of the real inverse Z transforms. So this is a big direction that we are moving toward. In general, let's use an X. So instead of using H, in general, I'm using XZ. We want to find out its inverse Z transform. We want to find out Xn for any signal. This in general. So we are doing this is we are doing an inverse Z transform on that. If capital Xz is a rational function, then we have hope to do some smart things like partial fraction expansion. And usually this is coming from LTI. It's a rational function anyways. So we got that BZ over AZ. B is a polynomial. AZ is a polynomial. We call that rational function is proper if an is not equal to 0. I count the order of denominator. If an is not equal to 0, then I exactly have the order of n. And also, m is less than n. And then we call this rational function proper. So the order of numerator, which is order of m, is less than the order of denominator, order of n. If this is the case, the rational function is proper, and there's no way for me to further do the long division. Right? I cannot do long division. It end up like this. If m is greater than n, I can always do a long division. So I'm divide something and make a polynomial. Then what's left is a rational proper function. Okay. So as I said, an improper rational function with m greater than equal to n can always be written as a sum of a polynomial and a proper rational function. Easy. What we do is doing a long division. So we have this. We got you divide it. You got this a polynomial, the C polynomial, and that is from order m minus n. When m is greater than equal to n, you will always have this order, right? Here, everything is a function of z to the power -1. So we got that. And then what you leave, this is a remainder of b prime or b1 here. And then you will get a proper function, proper rational function that we can play with. Now, the inverse Z transform of the polynomial can be easily found by inspection. And how? And what is the inverse Z transform of this guy? What is the inverse Z transform of a polynomial? Okay, I want to do inverse Z transform of x, right? Now I break that into two sections. One is this polynomial. The other one is this proper rational function. So it's a linear operation. Z transform is a linear operation. Inverse Z transform is also a linear operation. If I want to do an inverse Z transform of the first term, let me write out here the inverse Z transform what we will have is C0 delta n plus C1 delta n minus 1 plus C2 delta n minus 2 all the way to C n minus n times delta n subtract n plus n. Okay, that's it. And inverse transform of this is very simple. If it's a constant 1 and become delta n. C to the power negative 1, by shifting property, that's just one delay. So you have a delta n, then you have one delay is delta n minus 1. And so on and so forth. You have delta n minus 2 all the way to delta n minus capital M plus n. Okay, so this is the inverse transform of this polynomial. Very simple. Now what we have left here is this proper rational function right here. We also want to do an inverse C transform for this guy. And if you can't find that, you just adding those two parts, you find inverse C transform of X. Now let's focus on a proper rational function. Xz is proper rational function, B over A. So we write into this polynomial term. Since it's a proper rational function, we got this. N is strictly greater than M. Then what we can do is you write into this form. This is a function. It's a function of z to the power negative 1. Now this is kind of I multiply numerator denominator by c to the power n. It's a function of z. But you can argue it's the same thing. But we just like to write into this in order to discuss polynomial and to find the numerical results. What we do is we divide it both left and right by z. And then we, on the right-hand side, we end up with this rational format. And this is also proper. This is also proper because if you check with the order of denominator is n, the order of numerator is n minus 1. It's strictly less than the order of the denominator. Therefore, it's proper. So for this one, we are discussing with this one. This is a proper rational function as a function of z. Now we are looking at a function of z in order for me to discuss about the polynomials. Easy. Suppose I have distinct poles. The poles are P1, P2 to P sub n. They are all different, distinct poles. How many poles I have? Well, I have poles according to the polynomial on the denominator. So if you look at this term, the previous page, how do you find the poles of this guy? Now, this pole is not xz, it's xz over z. So the pose is to make this polynomial equal to 0. And then what you have is all these zeros will make the left term infinite. And those are the poles. And because the order is n, therefore I have P1, P2 to Pn, n poles. If all these poles, they are different. There's no two poles are the same. We call that n distinct poles. Therefore, I can divide that into a format like this. So we can divide into terms. Each term is A1 divided by Z, subtract a pole, P1 for the first case. Let's just look at the first one here. Okay. Because I have a proper rational function, if you divide into these terms, and each term in this green box, that should also be a proper function, meaning that the order of numerator should be strictly smaller than the order of denominator. Well, in this case, the order of denominator is 1, order of 1, just C subtract P1, right? Therefore, the order of numerator is 0, which means that the polynomial on the numerator is a constant. It's a constant A1. And I have here, the rest is the same thing. So the numerator is order of zero, order of zero. So it's just constant of A, has nothing to do with C. Okay. So what we want to do is we want to determine the coefficients A1, A2, AN. I write this in the format, but I do not know the actual number. So I want to find out those coefficients A1, A2, all the way to AN. The good thing is I know those are just numbers. These are not polynomials. These are just numbers. So we observe that if I multiply this left term here, by a factor z subtract p sub k. So this is just a factor that including one particular pole, pk. If we multiply by that, on the right-hand side, all these terms, smaller terms, will be multiplied by z subtract p sub k, z subtract p sub k, except one term in the middle, which z subtract p sub k canceled out. And this is exactly the term when the numerator divided by denominator. Denominator is supposed to have a pole at p sub k, so you cancel that out. Now, all these terms are still there because the poles are distinct. You will not be able to cancel that. Okay, so I have that. So in this case, I focus on that. I want to find a sub k's. How to find that? Now this is something that is entire thing is a polynomial. Entire thing is a polynomial, or it's a function of z. It's a function of z. Z can be any complex variable. I evaluate this function exactly on z equal to p sub k. Z equal to p sub k. So you plug in z equal to p sub k, and then this guy becomes 0, this guy becomes 0. So all these other terms are canceled out. What you left is only the coefficient of a sub k's. So I have this polynomial, which is you have your xz over z multiplied by this format z subtract p sub k. You evaluate at z equal to p sub k, and then you find out the coefficient a sub k. All the other terms cancel out. Okay. So we can do this for all different k's, k from 1 to 3 all the way to n. In that way, we find all these coefficients a sub k's. These coefficients, if I have two poles, they are complex conjugate of each other. If P1 and P2 are complex conjugate of each other, and then I have those coefficients, I can just find out the other coefficient. A2 is a complex conjugate of A1. I do not need to calculate that again. Okay. We know if the coefficients A's and the B's, let me put out here, these coefficients, and in this case, my numerator, denominator is A's. If all these A's are real numbers, then I have roots. Either you got a real root or you have a complex conjugate pair of roots. Here is, I have, either you have the pole is real, or if it's complex, you need to have a complex conjugate. So it just reduced my calculation by half. I only need to half of those coefficients, a sub k's. So this is the way we calculate the inverse transform with all these k's unknown, or all these a's unknown, And then the rest of the equation is that for each one of those, how are you going to calculate the inverse transform? Or by looking up the table. Because by looking up table, you know, if the denominator is only order of 1, it's very simple. You can find that. And in that way, we can find the inverse transform of this guy. But don't forget, you divide by z here. It's a function of z. And actually, you translate back to the function of -1. It's quite straightforward. And we can do that. So what we leave here is how to continue to do that. And of course, the second problem is, if I have a pole of multiplicities, if not distinct pole, n poles, how am I going to do with that? So we will see that next time.